I'm going to talk about C4, Verified Transactional Objects. I am Mohsen Lesani from University of California, Riverside, and this was a collaborative project with Liao Jia, Anders Kassier, CJ Bell, Adam Chipala, Benjamin Pierce, and Steve Denson. Okay. Atomicity is a well-known fundamental concept in concurrent programming. In its most basic form, a concurrent data structure provides atomicity for single method calls. So if you have a concurrent hash map, you can issue a put operation on it, and this put operation is going to be atomic. The clients will not experience or observe the interleavings that might happen. But if you compose multiple of these put operations, for example, here you have a transaction, you're doing two put operations for two different keys. This is not atomic on a concurrent data structure as we know it. The first property, single atomicity, single method atomicity, is known as linearizability. And there are many instances of these data structures in the literature. Log-free, log-based data structures often provide linearizability. But the second guarantee is called serializability, and it's not very often provided. In Java library, you don't have this. Transactional memory is a well-known data structure, we can call it, that provides serializability. And why do I consider transactional memory as a data structure? Because that's because we can see a transactional memory as a serializable transactional object. Right? You can see it as a map where you can get or read, or you can put, you can write or put, right? And you can have serializability for it. So if you have multiple operations in this data structure, that's going to be atomic. So these two classes are famous. The first one is very famous for efficiency. Linearizable concurrent data structures are usually very fast. Serializable data structures, on the other hand, are known for composability. Not very fast, but very composable. Modern data structures try to combine the strength of these two. So they use efficient concurrent data structures to quickly do lookups, and they use transactional memory to gain composability. A very well-known technique in this area is called predication. And how it works is that it composes a concurrent map with transactional memory. It uses the concurrent map to quickly map keys to references. So very efficient lookups. So you give it a key, it can quickly give you a value, which is in this case a reference. The subtle point here is that that reference is managed by transactional memory. Transactional memory, the maps this reference to predicates. And what predicates are just Boolean locations that store whether that corresponding key is in the data structure or not. So now how it works is that imagine the user has a transaction. It is executing two put operations that we just saw. For the first key, what happens is that we quickly look up the reference and then we access the predicate for it. We're looking at the transaction set. Maybe we are adding or removing this element, so we are flipping this predicate from true to false or the other way around. And for the second operation, you do the same. You find a mapping for the key to a reference, and then that reference is mapped to predicate. You can change it. Now, the smart design is that all of these are part of a transaction managed by transactional memory, and you get atomicity for the whole operation. So as you see, sorry, this image was fine at home, but this PowerPoint viewer doesn't like it. And I tried to fix it, but I couldn't. So what I wanted to show you here is that to design a predicated set, a lot of objects have to be composed in a hierarchy. So each one of these objects is subtle, the composition is subtle too, and more importantly, you should reason about both linearizability and serializability at the same time. So, in this area, protocols, algorithms are so subtle, and now we have to reason about two different notions of correctness at the same time. Our contribution in this project is a mechanized framework for compositional verification of concurrent objects that incorporates both linearizability and serializability reasoning. And we have mechanized everything that I'm going to talk about in the Cogtor Improver, and we released the library. Okay, so as I mentioned, everything about this project was formal. It took us a long time to verify everything here. But we decided that I keep the talk at a very high level. So no big deal. I'm going to just show you some diagrams. We're going to go over high-level ideas, and then you can, of course, read the paper. So let's start with the concurrent objects. How do we represent them? Well, a concurrent object provides an interface. For example, a counter provides the increment method. And the increment method is implemented on top of a base object, or the field object, if you will. In this case, the counter is implemented on top of a register. And the increment implementation is going to implement this method by doing multiple calls on the register object. For example, here it's doing a read, and then a compare and swap, and then based on that, it makes a decision, and then it do a recursive call. It does a recursive call. We capture implementations as interaction trees, which basically bind values to the result of method calls. You can have a sequence of method calls, and you can also have conditionals afterwards. The good thing about these objects is that you can compose them as you expect. You can use an object as the base object of another object. So you can compose implementations vertically on top of each other. So you have an object here at the bottom, we are implementing something else on the top, and we have a larger object. You can also horizontally compose objects. So here we have two objects, object 1 and 2. We're composing them together horizontally as a pair. The horizontal composition provides the union of the two interfaces, and you can use that interface to implement a high-level object. So with that, let us see how we can define linearizability. We capture linearizability as a simulation relation, a concurrent simulation relation, that tries to capture the same behavior for the concrete object and the abstract object. So what we do is that we basically capture this well-known notion of simulation for programs or interaction trees. For example, we prove that a concurrent hash map is linearizable with a map specification. And in the same framework, we capture the compositional properties of linearizability. We capture that you can horizontally compose linearizable objects. If you have object O1, that's linearizable with respect to O1 prime, and you have object 2 or O2, that's linearizable with respect to O2 prime, then if you horizontally compose them, the horizontal composition of the concrete objects is linearizable with respect to the horizontal composition of the abstract objects. This is a property that's well known as the compositionality property of linearizability in the original paper. But we also have other notions of composition. We have vertical composition. So if you have an object that's linearizable with respect to another object, or with respect to O prime, then if you compose an implementation on top of these two, then you still get the simulation. So the bigger object here, the bigger concrete object here is going to simulate the bigger abstract object. In the same framework, we have hierarchical verification for linearizability. So linearizability, as we defined it, has the transitivity property. So to prove that the concurrent hash map is linearizable for the map specification, we can do it in two steps. We can first prove that the concurrent hash map is linearizable with the sequential hash map, with respect to the sequential hash map. We need some combinators here that I'm not going to talk about, but basically you prove some sort of simulation here. And then the next step is to prove that the sequential hash map sequentially refines or simulates the map specification. And then by transitivity, you have that the concurrent hash map simulates the map specification. To aid the proofs of linearizability, we provide a proof principle that's very helpful in focusing the proofs and making them shorter and more manageable. So if we look at linearizability as some sort of simulation, then to prove linearizability, we have to first define some simulation relation between the concrete and abstract states. And these states are very involved. We have to talk about the pool of threads. So the state here is a mapping from thread identifiers to the program of each thread, and also the data state. We have it for both the concrete and abstract, and you have to define a relation for those. So that's usually a very large relation, and there's a lot of boilerplate definitions in there. We want to keep the focus, so we have a proof principle that lets us define 3 separate relations. And then after that, we have 5 separate, simpler obligations to prove. So we decompose the simulation relation into 3 pieces, and that helps us to break the verification into 5 separate obligations. I'm going to get back to this later at the end because there are a lot of details here, and I think it's good to go through that. But in this overview, I just wanted to tell you that there's a lot of facilities in the framework to capture concise proofs of linearizability. Okay, so with that, let us look at transactional objects. I mentioned that we have to capture serializability as well as linearizability in this framework. And now I'm going to show you how we do that, how we capture transactional objects. So what are transactional objects, by the way? Transactional objects are these special objects that have this method execute. And you can pass programs to this method. And then that method is expected to execute this program atomically. So in our framework, you can pass programs as first-class objects. So a method can get a program. It can inspect the program, it can interpret the program, it can instrument the program, add particular method calls, and re-execute the program if needed. And that's very central to the way we can define serializability. We want to be able to insert lifecycle methods of transactional memory at the right places. And this ability of being able to transfer programs is very important. So, in fact, in our framework, we can quantify our programs. We can define the insertion of lifecycle method calls without any ghost state. It's very important that we can take programs as interaction trees and transform them. With that, let's look inside. So what do we have in a transactional object? We have a base object, that is the transactional protocol object. This is, let's say, transactional memory algorithm. We're going to look at one of those. This is basically the protocol. And then on top of that, we have an implementation. That implementation has to insert lifecycle method calls at the right places in the user program, and then execute those calls on the protocol. We're going to look at each one of them in turn. So the transaction protocol is expected to have this interface. It has to define a method to initialize. It has to define a method to execute method calls M on the interface. So we have M of V on the interface, let's say map interface. Then there's a lift in the protocol that can execute it. And of course, there has to be method calls for abortion and completion of the transaction, commitment of the transaction. And this T that you see here is this thread local variable that can be threaded between these calls. Sometimes, for example, the timestamp has to be passed between these method calls, and that's how we capture it in a functional way. Here's an example of these protocols. We are looking at the transactional mutex locking. This is actually one of the protocols that we verified in our framework. We don't want to go through this. I just want to show you that it's a complicated implementation, but we can capture it as I described, and it does provide the interface that I showed you. So that's the protocol. Now we want to use this protocol to instrument the given user program. And again, because we can look inside the programs, we can transform the programs, we can easily do that. As you see, this instrumentation inserts init at the beginning, passes method calls to the underlying protocol, and then examines the result, and based on the results, it can call abort, continue, and at the very end commit. So these lifecycle methods are inserted at the right places. Here we go. We have a transactional object, and we want to define serializability for that. We have composition on specifications too. And we can define, interestingly, with these composition operators that we have, we can define strict serializability as a form of linearizability. So this is kind of surprising because a lot of people thought that it's actually the other way around. Linearizability is a special form of strict serializability, but in this framework, we actually captured it the other way around. We can capture strict serializability as a form of linearizability by just some combinators in these programs and transformations of programs that I mentioned. By that, we just need to use the same proof principle for linearizability that I showed you to show strict serializability. And that's exactly what we did. To verify the TML protocol that I showed you, we showed that these transactional objects that we create this way is linearizable with respect to some combinators applied to the map specification. But I'm simplifying this diagram a lot so that I don't show a whole lot of notation. But that's basically the summary. We can capture strict serializability as linearizability. Okay, great. So we talked about linearizability, we talked about strict serializability. We can capture both and we can prove both. Now I want to look at the use case that composes these two notions together. And that's transactional predication. We already took a look at this use case. Now I'm showing you just a little bit more detail here. Still, we have the locator on the left-hand side. You remember the job of the locator was to quickly map keys to references. And on the right-hand side, we have the TM, the transaction memory protocol. And the job of the TM was to map references to predicates, or in this case, values, because we are now implementing a transactional map. It's very similar in structure to a transactional set. And now I'm showing the implementations that we have to compose on the top. We have to compose two implementations on the top to implement this. So at the top, we have this interface, a program on maps, right? So the user can pass us a program on maps of type program map. So the first thing that we have to do is that we have to transform these program into calls on the base objects that we have, the locator and the transactional memory. And that's what this first implementation does. On the left-hand side, I'm showing a sketch of the code here. What it does is that it maps every one of the method calls to the map to two method calls, one on the locator and one on the TM. So on get, it does a lookup to find a reference and then performs a get on that reference. For the put, it does the same lookup, but then executes a put on the TM. Right? Very simple. With this transformation, we basically transform our program into a program. We transform the user program into a program of type prog of loc plus map, right? The interface of the locator union the interface of the map for transactional memory. Okay, great. So that was the first implementation that we had to compose at the top. And then we have another vertical composition, and that's instrument R. Instrument R is very similar to instrument that we just saw, but the only difference is that it does the instrumentation, this insertion of the lifecycle methods only on the right-hand side, right? So because we have transactional memory calls only on the right-hand side in this composition, right? So you have to apply instrument R instead of instrument. Otherwise, things are the same. So now we get the program of type prog of loc union TM, the union of the locator interface plus the TM protocol interface, right? So that TM is the interface of the transaction protocol. Great, that's exactly what the horizontal composition of these two objects provide. That's the interface that we get at the bottom. So these things can compose on top of each other. That's how we can capture transactional transactional map, transactionally predicated map. Okay, great. We could capture this implementation using horizontal and vertical composition, and that's exactly how we do it in the framework. Things compose nicely. But now the main question remains that how can we verify that this large object is going to be serializable? Before that, I want to look inside the locator. Locator was the object that we horizontally composed on the left-hand side. So the locator is, of course, an object that itself is implemented on top of a map, a concurrent map. So the locator is an implementation on top of a concurrent map. And you remember the job of the locator. The job of the locator was to quickly map keys to references. And the implementation is shown here. What it does is that it first, if you give it a key and say, look up this key, it quickly checks the map to see if that key is mapped to any value in the map. So we get an option value. We check if that's some value. If that's some value, we have the reference. We return that. But if we get none, then we create a new reference and then use put if absent to create a mapping from the key to that reference. It's very important to do put if absent because there might be other threads and they might look up for the same key and at the same time try to insert a mapping for this particular key. So we have to use put if absent. Put if absent is a method that puts the particular key and given value in the map, only it's absent in the map. If it does exist in the map, it returns the previous value. And that's exactly what we want here, right? So if it succeeds, it returns this P, right? And we return it. It always returns the value for the key in the map. So if you succeed, the value that we passed is exactly that value. It returns it, we return it to the user. If we fail and some other thread does it, it still returns the latest value, we return that. So you observe that locator is really a lazy map, right? So it's trying to implement a map that maps keys to values. The only subtle thing here is that it creates this map at runtime. Right? But once it creates a mapping, it never removes it. In fact, we could prove that the behavior of the locator is like an object that uses a static function phi that maps keys to values, or keys to references in this case. Right? We could prove that it's basically a lazy map. We could prove that it has this pure behavior, right? And that's critical to proof of the serializability that I'm going to talk about right now. So our goal at the beginning was to verify that this big object, this predicated map, is serializable. How do we do that? Well, we had these compositions on top of each other. The first thing that we do is using this purity property of the locator. So we replace the locator with some sort of pure object. I don't talk about the details so much here, but the point here is that it's really a function, right? Once it's a function, you can basically remove that altogether from the vector. It's like you don't have any object. And now the only object is the TM on the right-hand side. You can bring it to the center, and that causes instrument to be so instrument R is replaced with instrument. Right? And so what we basically did was that we could reduce this predicated map into a basic transactional map. And with the TM that we have, we know that this TM is serializable. We use its property. So we could basically prove by this reduction that the predicated map is serializable. I showed you animation and at a high level showed you how this can be done. But if you check the paper, this is done elegantly with an equational reasoning. So every step that I showed you is just a rewrite in the sequence of rewriting equational reasoning that we do. Okay, we get back to the nice figure. So we mechanized everything here in Calc, including the definitions and proofs and proof principles and the implementation of the objects and verification of those, the data structures and transactional memory. And these are actually reusable. So proof principle is reusable. We have multiple instances of proof principles that can be reused for later projects. And also the objects and transactional memories are used. Okay, so now, how much time do I have? Not much? Not much. Okay, so how much?
Zero.
Zero, okay. So maybe I stop here. Thanks so much, everyone.
You want to give time for the last question?
Yes, sure. Yeah.
So, we have time for questions.
This is about the I'm curious if you happen to know. Sorry,
Yes.
really, I'm happy to see it. I'm curious if you have thought about how this approach can be extended to weaker consistency models and linearizability or weaker isolation models and serializability.
That's a very good future goal. Right now, everything is strong, right? So we started strong, we define everything that composes on top of each other. But no notion of inconsistency. It's very interesting to see how we can do that. And we actually started to think about it.
Any initial thoughts or any early thoughts or?
Very tough. It's hard, right? So some of these nice abstractions are really rare. You have to find a way to build the evidence. Thank you.
Any questions? I have one.
Yes.
Can you talk a little bit about possibilities for automation? So a lot of the proofs that since you're doing mostly equational rewriting, do you see the opportunities to sort of go away from pure mechanization to sort of automating some of these?
Well, very good question. So in particular with the proof principles that I kind of talked about in the overview, but I didn't have time to present the details for. With this, there's a lot of chance for automation because the structure of the proof is known. We have 5 obligations. And like for example, actually this is a good slide. This is for stepping. So if we step, what sort of properties we have to have? We have to be able to step in the abstract too. Certain relations have to be kept. Right? So there are separate obligations, so 5 obligations. Each one of those 5 obligations is broken into smaller assertions to be proved. And we can automate those. So we didn't do that, but I think there is possibility to capture that. But in general, proofs of linearizability and serializability are really solid. So I don't want to promise something that's impossible or almost impossible. Some person has to be there unless one of these agents that they have created helps us, right? But I think probably human is in the loop, still in the loop. Okay, great. Thanks, everyone.